Good morning, everybody. So, welcome to be at this OPAL-RT learning journey about the product features ARINC 429 and AFDX. So, I would like to present myself as a presenter. I'm Mathieu Hainaut. So, I'm the offering manager for the division of the aerospace market at OPAL-RT. So, I'm the coordinator between the necessary of the market of the aerospace. So we'll have a quick introduction of the protocol that we offer, and especially we'll look at the two protocol ARINC 429 and ARINC 664, also known as AFDX. This is really dedicated protocol for the aerospace. And we'll conclude with a short conclusion and a question period. So like whenever you have any question, there's a pool where you can ask question on the application of the GoToWebinar, and we will respond to those questions at the end of the presentation. The presentation will be around 20 minutes. So if we look at the OPAL-RT protocol, like the architecture of the OPAL-RT system as a real-time platform is really like to take an electrical network or airplane models where we will run on a real-time architectures, both shared between CPU and FPGA, mainly CPU for the aerospace environment. And those real-time architectures will actually like transfer all the necessary data to your unit under test, which is your controller, through like some IOs and also communication. Like in aerospace, we see a lot of communication dedicated between the model itself and the unit under test. So if we look at the native supported communication protocol at OPAL-RT, so we have many offers, like we have actually more than this list I will show you. But for the aerospace, what we usually saw is like CAN communication. So basically we have a card and all the protocol natively on the software called RTLab. We support for sure like TCP/IP, UDP, all those kind of protocols. We have some Modbus. We have like all serial communication as well. And sometimes we have also specialized bus like the SIM-bus protocol that we can see. If you have other protocol that you don't see in this list, like probably we support that as well, just like a partial list of what we usually saw in aerospace. So today, like we will mainly focus on what we saw as aerospace dedicated and specialized communication buses, which is the MIL 1553 that we support. But today the presentation will be on the ARINC 429 and the ARINC 664, called also AFDX. So this is like usually whenever we have like a unit under test from the aerospace, like one of those three protocol are mandatory. So if we start with the ARINC 429, it's actually like a protocol that's been developed in the 70s. So it actually is not quite new, and it's still widely used in the aerospace industry. So like actually like from the beginning at OPAL-RT, since we work with the aerospace industry, like this one of the first protocols that we developed. Actually, what we did is like we redo the driver like 2 years ago in 2029 to like to be more incorporated in the RTLab environment. So if we look at the structure of the 429, it's like a 32-bit messages, and it's specified as a 8-bit as a label in octal. After that, we have 2 bits as SDI that is used by the customers. We have 19 bits of data, which could support like a binary coded decimal, BCS, discrete signals, and binary number representation, BNR. So basically you have a mix and match in here on the 19 bits of whatever you required on that. You have a parity bit at the end, and you have the SSM as well. A parity bit here and the SSM there. So at OPAL-RT, like now the supported card on all new application is the Abaco RAR PCI Express. So mainly OPAL-RT always use PCI Express based cards that actually fit on our real-time platforms. This card have a wide variety of configurations. So basically when you order it, you can have like the two port, actually two RX and two TX. So actually this is the combination that we have in this card. And this a single card can go up to 16, so 2, 4, 8, and 16 channel per card. If you need more channel than that, like it's possible to add more than one card per system as well. So the way that we work on the new protocol of the ARINC 429, like we actually make make use of what we call the DL architecture. So mainly, all the protocol was embedded in the OPAL-RT Simulink environment. So OPAL-RT, the software called RT Lab, and RT Lab is using Simulink as a modeling tool. We put all the driver functionality and configuration into the Simulink environment at first. Since 2019, we migrate all architecture more and more to the DL architecture, which take some configuration externally of the model because we don't change them on the fly and is not needed real-time performance. And we put this configuration into the RT Lab environment, so externally of the Simulink model. So that will lighten up the model size as well, and it make me more comprehensive. So this is what we do for this protocol, and actually like how you do a link between the model and the driver, which is configured externally, is with some need block called up output and up input. So basically everything you want to change, like the data or the SSI, the timestamp, like you put those blocks with the naming, and then after that you link them to the architectures. So like it's really done by the GUI, like the configuration. That's also allowed to have like an API. Like we prefer a Python API, but you can also use C API to actually like make the connection or address or configuring the driver as well. So if you prefer to have like a more structured like coding sequence to manage your ARINC 429, this is allowed. And also like all changes could be done through the GUI called RT Lab. So how it look like? So like this is like some print screen of like the RT Lab software. So when you have a project like the ARINC 429 here, and you have this Simulink model, ARINC 429 example model, this is like the Simulink models. But if you want to add functionality of the ARINC, you just have to go to the IO interface, which is the previous deal that I mentioned, and you add new IOs. And then you select from a list of different type of IOs. It could be like standardized IOs and a lot of communication. So if you see here, we support ARINC 429, as well as other protocol for the power systems. CAN is something that you might use, and we have a wide variety of communication through the deal. So we select 429 in this case. Then after that, you have to configure. Like you configure two things. First, you configure the board that you have in your system. So you have the cards here, the RAR, but actually here you see like we done some tests with up to 4 boards in the same system. And it's just a matter of like actually adding a board through the UI here. And then we'll see later that we add messages as well to the board. So when you add like a board, you depending on the configuration you do, like you will have different TX and RX channels. We can name them as well with different naming. In here, we have a board with 4 channels. So it's a configuration of 4 TX and 4 RX. So in the configuration itself, like you define after that the baud rate, is it like a high or low? Do we enable the parity on this channel as well? Actually, we have some feature for testing, so the internal loopback, so this could be enabled for testing at first when you test your environment. You define like a channel numbers that would be reused later. And we have some buffer as well as an example for the receptions. For the transmit, like actually same thing, we have the baud rate, the channel number, the parity. We can actually like inject some error. So like sometime when you do testing your unit under test, you want to add functionality to inject errors. So this is where you enable that or not. And like you have errors, and actually you enable the external transmission. So basically you can like the RX is always enabled, so you will sniff what's going on. Transmission, you can like from the UI enable and disable during transmission, the transmission. So then after that, when the board is defined, you define all the messages. So when you define the messages, you will first set, is it like a transmission, something I want to send from my simulation, or something I want to read, so the receptions. You select the dedicated board and which channel it will be used. So you select this message is linked to which board. Then after that, like when you define like a message like here, like a TX on one card and the transmission, you have this GUI that will pop up, and this will give you like a visual of your message. So basically here we have a mixed type, and in this message, like with the button here, plus and minus, you can add like a data structure. So basically I'm saying that, okay, I have BNR from this bit to this bit, and I have some discrete afterwards. So like you can either have a whole set of data. Keep in mind that we have also raw data. So actually you can define the message as a raw data. So instead of like doing that through the GUI, we send everything back to the Simulink environment, and you reconstruct binary like your 32 bits in there, and we just like forward the raw data from the Simulink environment to the drivers. So like there's no configuration for messages anymore in the UI. Then after that, you have flexibility on the SDI SSM. Like, so basically like for the SSM and SDI, like do you want them, especially for the SSM, like do you want them to be dynamics? So dynamics mean that you can control them dynamically through the to the Simulink environment as well. You have also enable cycling transmission. So either the model will trick. So basically, I would call that the schedulers. So since you have a real-time environment, you can actually ask the system to send a pulse from a clock in the real-time simulation to actually like build the scheduler internally of your Simulink models. Or if you want to do a quick test or it's good enough for you, you can do a cyclic transmission. So basically you click on that and actually you define what is like the refresh rate of this messages. So you just select what you want. Yeah, and also like here you have like some enduring data value. So basically you define the bit, but internally of this UI, you can say like what is would be the min and the max, and especially the gain and the value offset. So basically that's help you to start from a binary numbers to like an enduring values directly to the Simulink environment. So when you start defining gain and offsets, especially, you expect that the Simulink model will send something like altitude or temperatures, like a real engineering values, and the driver here with this configuration will transfer this gain and offset to put that as a binary code. One that is done, so we configure the driver internally of the GUI. You need to make connection between the Simulink environment and our system. So like with the up input and the up output that you put in your model, you start like actually like defining. So basically under the ARINC, you have all the data structure that you create. So then after that, you go to another page called configuration. And then in configuration, you will have these data structures and you will start like pointing out like what is the pointer of each value that you want to be controlled in this environment. This usually, for a few of them, we do that manually, but I cannot strongly recommend enough that by having a name list, you can easily use the API to make those connections. That will speed up a lot your process. So that was all for like the ARINC 429, like the implementation. Now we go to the AFDX. So AFDX is a newer, I would say, avionic full duplex switch Ethernet. So basically, we bring a more Ethernet-based messages to the environment of the airplane. So this is like quite of new, been developed by Airbus. So it's a really proprietary to Airbus. So Airbus is like more and more we saw them in their project, the FDX one, but that doesn't mean that you cannot see FDX on other type of plane as well. So it's really like to bring like a full duplex environment, not like a two-wire like like 2-wire buses. That's the ARINC 429. Like now we have like a full duplex buses here. What is neat is like you can have like the Ethernet wiring connection, and they also support like fiber optics if required. And what we usually saw is like the data type that we have in the AFDX, like the UDP, sampling, queuing, the ACP, like a point-to-point UDP, IP, and MAC. So basically, you have like a more like a sampling and a queuing as a bus, or you can have actually like two devices that talking to each other with UDP on IP or MAC. So what OPAL-RT refer is we support the IIT cards, and actually it's the PCI C64-V2 cards. That come with two buses, and these buses like could be like we can change the socket, actually the same price for both of them, but you have to define if you have a copper cable like the RG45 standardized internet connections, or more like a fiber optics. This all those selection are just made by the transceiver here and the outside of the cards, but it's an option that you can have. But yeah, it support like up to 1,000 megabytes of full duplex internet link, or we can use a SFP as well as fiber optics or coppers. But like really the interesting thing here is we support the ARINC time code encoder. So basically you can have like a source of ARINC as well for the timestamp. And we changed a little bit the way we configure the system in there. So instead of like using all the GUI of OPAL-RT, we directly use the GUI of IET. So from IET, like we support the flight simulator GUI. So that's the configuration of the driver itself will be done through the AFDX IET card softwares. So we'll see that a little bit later. So basically here what we have is like the driver configuration as you define through the IT flight analyzer all the input or the output. So basically I have like you had a cards, you define which channel that you want. So it's either one or two like you will use, and you define the up output and up inputs in the GUI. So you define like here the network A and B, the sequence. You will define as well like as the data type, the messages, the IP address through the analyzer. And then what you do is when everything is configured, you go to the thing and you export the device's configuration. Actually, it will be a binary file, and it's either like a .hex, which is the old format, and the new format, like from the latest software, is all ADC. So it's a binary file that have all the configuration of the driver that you define in IET flight simulators. And after that, from the GUI in Simulink, you import this file directly to your configuration panel in the Simulink environment for the FDX. So once you do that, like you've been using the blocks from our tool sets for configuration. So you import the binary file of the driver configuration, and then after that you add to your system all the status blocks. So if you want a general status on the cards or a general status on the messages or a bus, you have those two status that will give you like some count if you have errors on each buses. And then after you have transmit and a receive block. So from the configuration, you had those blocks. So basically, if you have like many messages, like you add one block of each messages that you have in there in your models. At the end, it's look like a little bit like that. Here, like this is the demo model that we send with the systems, and it's actually like 5 messages that we send and 5 messages that we receive. And actually, like this is all the data type that we have. Like we saw that we have a ACP, so like a UDP, IP, and a MAC, and we have the queuing and the sampling. So basically, like the demo model that we have everything to the wide variety of signal that is possible on the FDX. So you have the configuration here, and also you have all the status. So from the model, you have everything, and then you can start building and actually like acknowledge like a wider bus configuration. So this was it for the 64. So basically, as a conclusion, like OPAL-RT bring you like the RT alignment environment connected to the real-time simulators. We have like different real-time simulators, and into those simulators, we add like PCI cards for your needs of protocol, like in here the ARINC and the AFDX. Note that we have a limited number on our standardized simulators, like up to 4 PCI Express cards into that. If you need more than 4 cards in your systems, we always have the possibility to have a PCI expansion in the system. So we have like a other add-on, other accessories to add like a bus of PCI that can go up to 11, and we can stack them as well. So like there's actually no really limitation on the number of communication that you can have in the systems. So that's conclude my presentation on the OPAL-RT offer on the AFDX and the ARINC. So if you have any questions.